righty. First thing first, I posted on the Moodle page the final 40 points of our third test. It covers things on the polymers and plastics and a little bit on the biochemistry stuff. Now, what I did was I set it so that it had to be done by next Wednesday. So there's a week from today to complete the third part of the third test. So, yeah, that's right, 11:30. That would be, I guess, Wednesday, November 20th is when, that was at the 20, what am I talking about? 25th. Wednesday, November 25th is Wednesday of next week. So by 11:30, please make sure you have completed part 3. Then after we have turkey, we will have a final that I have, depending on what we finish covering, will be on the stuff we're talking about today and Monday, of course, and it'll be on Moodle again. Just click on there. It'll probably all be on there at once, whatever. I haven't decided exactly how I'm going to do it, but pretty much the same kind of thing. Maybe it'll, I don't know. I haven't decided how it's going to play out, depending on how many slides I cover while I'm standing here blathering with wasting time, I guess. All right, so what we're going to then do is move into a new topic of discussion. So probably what I should do is put our new topic of discussion up now. Let me again turn to my spectacles. Just wait. When you guys get older, you'll have to do things like I'm doing now because you can't see. I don't know what happens to all these sorts of things. Okay, so I want to get this and get the slideshow from the beginning. What we're going to spend today on is a discussion of the E word. And the E word is a very important aspect of all chemical processes. That is the relationship of energy in chemistry. Okay, what we're going to do first, though, is we're going to spend a little bit of time with just some introductory information about energy in general and the science of energy. I think I have mentioned in the past to you the fact that energetics are certainly the reason that humans endeavored into doing chemistry in the first place. There's pretty much no doubt about that. The origins of chemistry, I would say, was when humans tens of thousands of years ago began to use fire to make their lives better in many ways. And really, there was no interest at that point in understanding what was going on in this combustion process, which was generating all this energy. What was realized, of course, was the utility of the energy that could be released from the fire. So it's really kind of ironic to me with regard to the fact that 10,000 years ago, the driving force of the beginning of chemistry was harnessing energy from materials. Even to this day, I would say the driving force of chemistry is harnessing energy from materials. So even though this has been this kind of bookending the history of human endeavoring in science, or at least in particular in chemistry, still the overall motivation, or at least one of the overall motivations of fooling around with chemistry, is to release the energy that is stored in the so-called chemical bond. So the connection between atoms somehow supplies a source that we can tap into to retrieve the energy that is stored in the chemical bond. Okay, so again, that's going to be the focus of what we're going to be discussing with regard to energy, how it's related to chemical processes. But before we do so, let's just make sure we're all on the same page. Let's just talk a little bit about energy and some of the basic definitions of energy. So first of all, just what is energy? Well, this is really a kind of a circular argument, because if you look up what heat is or what work is, it'll say the ability to use energy. And if you look up what energy is, it says that very typically, in even a primer used for youngsters just beginning to learn about science through the dictionary definitions and all these other sources that you might turn to find out what energy is. Almost invariably, the definition of energy involves words of these types, is that energy is the ability to do work or supply heat. Now, it's interesting that it lists these two aspects of what we want to do with energy. This is the driving force, the motivation of humans to gather and harness energy. It is the fact that we desire energy to heat something up or heat us up, heat a building up, protect us from the elements themselves, or to do what we call is work. And we're going to make some kind of differentiation between what work is, but I think we all understand that means pushing and pulling and moving objects around. So this requires energy to do. So this definition of energy kind of encompasses what humans want to do with it. Now, if we stop then and give this definition, if we break it down and think a little bit more in depth about what energy is, and we turn to physics, and we turn to the number side of physics, which I mentioned many times over, is what it's all about. The whole premise of science is to attach a numeric relationship to the phenomenon we observe around us. So if we attempt to ascribe some numeric relationship to energy, the first thing you would learn is that energy is not a vector quantity. And let's remind ourselves of what I mean by the vector quantity. A vector quantity is a measurable quantity which has a numeric component, a size to it, but as equal important, it also has a direction associated with it. And the many numeric or vector type quantities that we had discussed earlier were things like position in space, where you are located. You actually need a distance and a direction to know where an object is located. The velocity or change in distance, if you like, with time, acceleration, the change in velocity with time, force, which is the mass-weighted acceleration of an object. All of these things require not only a numeric value, but a directional value. There are other things that have this same kind of properties that we talked about as well, of course, like fields in physics, the gravitational field, the electric field, the magnetic field, momentum, the mass-weighted velocity has a direction along with a magnitude associated with it. Okay, so suffice it to say, many very important quantities in science require these equally important components in which to, if you're intending to specify them. Energy, on the other hand, is what we have called in the past a scalar. Scalars have magnitude only. And of course, energy is not the only scalar that is present in physics. Other important scalars include time, mass, volume, things like voltage. These have a magnitude without, well, voltage is very closely related to energy, by the way, but in any event, these are quantities that only require a magnitude to specify them. So when physicists set about to solve problems to understand the physical world about them, in many regards, energy is a convenient tool to use because you could only need to worry about a numeric quantity and not so much about a directional quantity, which just in many instances complicates the problem. So if we can get away without worrying about the directional component, it makes dealing with this issue a little bit easier. So that's sort of the big picture, at least from a scientist's point of view, with regard to quantifying energy. So this is just some of the basic ideas that I or other pattern recognizers in the physical world around us would try to think about when we're going to begin to model the energetics of a situation. Ultimately, what we want with energy is, as it says here on this statement, the ability to move things around or the ability to warm things up. Now, of course, the opposite might be true. We might wish to cool things off as well. And if we want to cool things off, of course, we're going to, in some way, have to remove energy from the object if we want to cool it off. So what this is implying, of course, is that temperature is closely related to energetics. And what I would say to you is that it really is one of our few handles on energetics. We actually have a few others. But if you want to gauge the energetic content of an object, there are only a handful of ways of doing the measurement of how much energy a particular system possesses. Probably the most simple way to measure the energy a system possesses is to look at how it is moving. And there's a very straightforward relationship between the velocity an object possesses and how much energy is required for it to move at that velocity. This is one of the most celebrated equations of our numeric analysis of the world around us, and that is that the kinetic energy is 1/2 mv squared. So we can gauge the energy content of an object simply by how fast it's moving. Now, this has to be a mass weighted gauge of how much energy it possesses. It's not just a simple velocity idea. Because, of course, a mosquito can fly at maybe 40 miles an hour or something like that. I don't really know. Maybe that's a little fast. Maybe we'll go with 30 miles an hour. A mosquito can fly. But if it flies into my arm, I'm hardly going to note because the amount of energy it imparts into my arm is pretty minuscule. However, now if somebody throws a baseball at me at 30 miles an hour and it hits my arm, I think I'm going to definitely note a much more significant impact of energy striking me simply due to the fact of the mass of that baseball is so much greater than the mass of the mosquito. So there is some mass weighted inference to the energy content that an object possesses. But having said that, let's just ignore the mass part of it for the moment. We'll come back to that later. We can tell that an object which possesses more and more energy will move at a higher and higher rate of change of displacement with time. So that is obviously one way we can gauge energy. A second way, particularly in the electrical world and the charge world, is to measure something about the potential difference that is possessed by the object, how much charge has been separated from the even distribution of charge, and what we call this is the voltage. So the more and more voltage present in an electrical system is telling us something about more and more energy possessed in that system, which can be later converted into this heat or work to do things that we want with it. Now, just think for an example, a lightning strike. There's an incredible amount of charge separation as the clouds rub off of each other over and over again. There's many electrons rubbed off of cloud A and onto cloud B until the charge separation between the Earth and the cloud becomes so great that it has to eventually force the air, which doesn't want to conduct, into conducting the electricity and redistributing the charge more evenly. So as we're all, of course, aware, there's a huge amount of energy in the strike of this lightning bolt as well, because of this charge separation. So first way we can measure energy content is possibly by how fast an object is moving. Secondly, we can measure it through some electrical means like the voltage of the system. And third, and probably most importantly, certainly in the aspect of chemistry, a way of gauging the energetic content of a system is by how hot it is. And we do that by measuring its temperature. So when I'm measuring the temperature of an object, I'm somehow getting a sense of the energy content of that object. Of course, when water is boiling, if I put my hand in it, I'm going to be imparting a huge amount of energy in my hand, so much energy that it's detrimental to the chemical makeup of my derma itself. If I put my hand in room temperature water, of course, I can leave my hand in room temperature water because the heat energy that's being exchanged between the bath and my hand is such that I won't invoke any weird chemical changes in my hand due to that energy. So of course we sense this energetic content by putting a device known as a thermometer down into the material, and it gives us a reading, and from our everyday experience, the reading indicates to us something about the energy content of that system. And of course, the energy content is then closely measured in terms of temperature, is closely related to the heat part of this definition. Now, the one with the work part of it, I would say in that instance, it's the velocity or movement of the object. When I'm doing work on an object, I will impart motion on it. And then I can gauge from the amount of motion that the object gains something with regard to the energetics that have been supplied to that object. Now it turns out that really it works both ways. I can ascribe something about heat with motion, and I could ascribe something about work with temperature. I can interrelate them. That's because all forms of energy, as we will see, are interchangeable. So that'll be another piece of this energy puzzle, which we will unravel as we move forward on our slides here. Now, let's move on to some other definitions and things of importance to what we are going to do when we're in this energy discussion. We're going to classify energy in one of two types. And those two types are either the usable form or the harvested form. So essentially what we do, if we, as it says here, energy is the ability to do work or supply heat. We have to get the energy from some other source to do work that we want to be done with it. We have to harvest energy from some other source to heat something up. So what we're going to then do is differentiate these two particular categories with regard to energy. The first will be kinetic energy. And as the name kinetic implies, kinetic is a word that means moving. So kinetic energy is energy of motion. And I show here this car, moving by the impart of energy to the wheels of the car. Well, how do the wheels of the car move and give this car kinetic energy? It harvests the energy to make the car move from a source of energy. So the sources of energy that we use to make motion will be called potentials for energy. So the idea of the second name is that energy of the potential form can be converted into energy of the motion form. Now let's again be very clear about this, and I've said it a few times already, but let's say it again. Energy of motion is what we want. We want to put things in motion, whether or not I'm doing work to them or I'm trying to heat them up. We will make this distinction on very shortly upcoming slides. So I want motion, and if I want to put more energy into an object, I want it to be moving more dramatically, as we will see. So in order to get objects to move more dramatically, I have to feed them energy. And the energy sources that I feed to invoke motion are potential energy sources. Okay, so I will classify then potential energy as the energy of position. And I want to get rid of my little thing down here, I think. Or I'm going to classify energy as being stored. Now, in many regards, these are exactly the same thing, and I'll try to make the differentiation with them for you. They are either energy of position or energy being stored. Now, maybe as an example, let's think about placing an object on the shelf of a book stand. I have a book stand and I put an object on the shelf. Say the book stand has 3 shelves. I put an object on the shelf, on the lowest shelf closest to the ground. It has now stored energy simply by me putting it on the shelf. What is the form of energy that is stored? It is stored due to the gravitational difference between the location of the shelf and the ground below it. I can convert the energy stored into that object into motion by pushing the book off the shelf. It falls to the floor. Now, if I put the object onto the second shelf, higher up than the first shelf, I have stored even more energy. How do I know that I've stored even more energy? If I push the book off the shelf, it falls to the ground, and when it hits the ground, it makes a louder sound when it gets there than it did when it fell from the first shelf. So I'm implying from the sound that the book made that there was more energy when it fell from the second shelf than there was when it fell from the first. And of course, if I did some clever measurements of how fast it's moving and other things of that sort, I would find that indeed it did possess more energy when it reached the floor when it fell from the second shelf compared to how much energy it had when it reached the floor from the first shelf. I don't think this is surprising anybody. Now, of course, then if there's a third shelf and I put the book up on the third shelf, which is higher than either of the first two, I have stored even more energy in the book. And now, of course, if I let the book fall to the ground, it'll make a big loud clap noise when it hits the ground because it's moving when it hits the ground at an even greater velocity than it was from the second or first shelf. So the position where I have placed the book in the field of gravity stores various amounts of energy. So this is the relationship of position in this idea of storing energy. Now, of course, if I put 2 of the same exact books on the same exact shelf, they have both stored exactly the same amount of energy. So there is this relationship where if you're at equal potential, we say, but I'm at the same height in the gravitational field, I'm storing the same amount of energy in the objects as long as they weigh the same. So remember again, this idea of the actual energy that you ultimately possess is going to be a function of the mass of the object. If I put a huge 10-ton weight on the third shelf and it falls off and it hits me, I'm in trouble. But if I put a 1-pound weight on the third shelf and it falls off, it might hurt a little bit, but I'm going to be in less trouble because it will have less energy due to they will move at the same speed. That's what gravity does. But the one with the greater mass will store the most energy in it due to its position in the gravity. Okay, so there's other relationships which I can take and make the same argument. Let's take a dart gun. I take a dart gun and I push in the dart, and then I put the dart gun in my pocket. I have stored energy in the dart gun. I can leave the dart gun in my pocket for a day, a week, a year. I get the dart gun out after a week, pull the trigger, and I can convert the stored energy into motion energy when I pull the trigger on my dart gun. Now, the other thing you can envision is that maybe the dart gun has clicks. I click it in once, and it only compresses the spring in the dart gun a little bit. So then when I pull the trigger, it shoots out only a little bit. Now, maybe if I push it in harder, I push in the spring even further, I've stored even more energy due to the compression of the spring. So now when I pull the trigger, it flies a little further. Now, it could be that I can push it in even harder, compressing the spring even further, so that then when I pull the trigger, it flies really far. So that would be how I would describe the position of compression of the spring to have some impact on the amount of energy that I'm storing in the spring when I click the dart into the dart gun. Okay, now one more thing before we turn the page that you should notice here. If I store energy on the bookshelf, or if I store energy in the dart gun, I personally must do work to accomplish this fact. Here's what I mean. The book is on the floor. We'll say it has no energy when it's on the floor. I put it on shelf 1. It has stored a certain amount of potential energy. Shelf 2, more potential energy. Shelf 3, even more potential energy. But in order to get it to shelf 1, I must do work myself and expend my own energy to lift it in the field of gravity and place it on that shelf. If I want to put it on the second shelf, I must expend even more work. If I want to put it on the third shelf, I must expend even more work. Same thing is true with my dart gun. Pushing it into the first click, I have to push a little bit. Pushing it to the second click, I have to push harder, doing more work. Pushing it into the third click, I have to do work even harder. And as a matter of fact, as you might be able to envision, nature works in such a way that this is exactly conserved. The amount of energy I store when I move the book to the third shelf is exactly equal to the amount of energy I did to put the book on the third shelf. The amount of energy I store when I push the spring into the second click on the dart gun is equal to the energy I used to push in the dart gun. So as we will learn, energy is a conserved quantity. You put it in, it's in the bank, it's in the stored form, then you can harvest it from the stored form a little bit later. Okay, so let's look at some forms of energy that are out there, and we will classify these various forms. I already mentioned a spring as a form of energy. Another form of energy that, of course, we can harvest is light. And the general definition or the general terminology that we use for light, as we have talked about, is electromagnetic radiation. Electromagnetic waves contain energy, and this energy we will classify as potential energy. So when electromagnetic radiation bombards the Earth from the sun, it is absorbed in the photosynthetic process of the chlorophyll in a leaf, and it's transferred into the leaf. Ultimately, what is the energy of the electromagnetic form that is absorbed from the sun converted into? It's converted into a chemical bond. And it is now stored, instead of in the form of light, it is stored in the form of a chemical bond. So that's a story for down the road here. Of course, not only is electromagnetic energy a storage form of energy, so is electrical energy. Anything I plug into the wall, I make a light bulb light up, I'm converting my electrical energy into light energy. I plug into the wall and I heat up the coils of my stove. I'm converting my electrical energy into heat energy. I plug into my wall and I turn the blades of a fan in my room. I'm converting electrical energy into mechanical energy in that particular case. So again, electrical energy is a form of stored energy. And again, I could even think of how would I measure the energy of position in this context? It would be the voltage. The more voltage I have in the electrical energy, literally the implication is the further charge has been separated, meaning the more I start with neutral charge, I make maybe a unit of plus 1Q, and then an object is plus 1Q charged, then somewhere else something is minus 1Q charged. So there's a certain amount of voltage in that charge separation. What if instead I made it plus 10Q? Then, of course, if something became plus 10, somewhere else something became minus 10. So now that's even a greater separation of charge from the neutral point. That implicitly has a higher voltage associated with the greater amount of charge separated. So this electrical energy is potential energy, and the magnitude of the potential energy is somehow related to in a measured form, in the voltage that would be telling us something about charge separation in that originally neutral situation. Okay, so this is two forms of energy. How about the form of energy known as the gravitational energy? I did talk about this one already when I was talking about my bookshelves. We all understand the concept of what I meant. The higher up on the bookshelf I place the object, the more energy it possesses, and I can convert that energy to the usable form of motion by removing the shelf from underneath the book. And now the mass attraction of the earth to the book compels the book to fall to the earth. Okay, so and we can envision the higher up in the gravity field that you place the object, then the more potential energy you're storing in the object. Now, again, this has to be mass weighted. If you lift up a feather way up high in the sky, it won't really have a lot of energy stored in it compared to, say, lifting up a 10-ton weight to the same height. That will certainly store way more energy. Now, the other thing to think of, how much work I would have to do to lift the feather up to a certain height compared to how much work I would have to do to lift the 10-ton weight up to the same height. It's very obvious that I would have to do more work lifting the 10-ton weight, and this goes right hand in hand with what I'm saying. The energy stored by the field of gravity is exactly equal to the energy I put in to lift a particular object to a certain height in the field of gravity. Okay, the next thing a source of energy or a storage form of energy is in the nucleus of an atom. Remember, the nucleus is where the protons and the neutrons reside. The neutrons are kind of the Velcro, keeping the positively charged protons all held together. So there is a huge amount of energy required to hold a large collection of nuclei together. Now, it turns out to hold a single atom together, not so much, but we never deal with single atoms at a time. Even in the pile that fits in the palm of my hand, there's 10 to the 23rd atoms present in that pile. And if you begin to release the energy of the nucleus by starting to rip apart nuclei of all 10 to the 23 of those atoms, you're going to release cataclysmic amounts of energy. So there's lots of energy containing the positive charge of a collection of nuclei into the nucleus of the atoms that are surrounded then by electrons. Okay, so most important to the discussion probably for what we're talking about here is another stored form of energy, and that is the form of energy stored in a chemical bond. So the relationship that holds atom A to atom B in a molecule is the connection that the electrons provide that are shared between atom A and atom B. The shared electrons, of course, as we've talked about, constitute a chemical bond. And by ripping apart the molecule, as we do in combustion processes, we're releasing this energy that is stored in the form of the shared electrons. Now, what are we converting it into? We're converting some of it into heat because the fire is hot. We're converting some of it into light because the fire is glowing. We're actually even converting some of it into sound and actually converting some of it into pushing the air around the fire out of the way as the materials that are burning are changing from a solid into a gas. They have to squeeze their way into the atmosphere, and in order to do that, they have to make their own room in the atmosphere, so that they have to push other things which are in the atmosphere out of their way. Okay, so now we've pretty much exhausted our forms of stored energy. The remaining two are the ones that are of interest. They're the ones in the definition of energy. So mechanical energy or work, the ability to move objects around, including my arm up and down, or a car driving me from here to Slidell. The car has to do work to drive me to Slidell. And that is what we would term as mechanical energy. And that is energy of motion. And then it says these two examples show, I'm sorry. Now I'm getting what I'm saying here. Just making sure I'm reading this clearly. These two objects are using chemical energy to convert to mechanical energy. Now, the object on the top is really the engineer, and now I realize what's going on there. The object on the picture on the top right is the engineer or somebody driving this train, putting fuel into probably coal into the furnace that is converted into steam, which powers and pushes pistons, powering the locomotive down the tracks. So we're showing how the chemical energy is being converted into the mechanical energy to move the train down the track. Now, of course, not only are we making mechanical energy as we burn the coal to move the train, we're making a copious amount of heat energy. As a matter of fact, this is one of the horrible side effects of our devices that we generally use to make mechanical energy, particularly when we use combustion engines. And the name combustion engine kind of says it all. I'm going to burn something to make mechanical energy. So when I have a steam engine, when I have a car engine, when I have my lawnmower engine, or anything of that type, I'm ultimately burning a fuel to convert to moving the car down the road. Well, unfortunately, a vast majority of the energy is completely wasted in that process. Why? Because most of the energy is not converted into the mechanical form. Most of the energy is converted into heat. So when I burn things to harvest the energy from them, the energy ultimately is going into the form of heat. I use tricks to make it mechanical, and these will be tricks that we will say some things about here going forward. But ultimately, so much of it is wasted that engineers, mechanical engineers who look closely at these sorts of things recognize that the internal combustion engine of a car is about 30% efficient. 30% of the energy we get out of burning the gasoline is converted into moving the tires down the road. The other 70% is wasted by far and away, mostly in the form of heat. We can't convert all the energy into work. We convert 70% of it roughly into heat. Now that's okay on a cold day because we can blow that heat through the compartment of the car and keep us warm. But generally speaking, that is not what we want that energy going into. We want it going into driving the tires, not heating up the engine block. It's so bad that we actually have to cool the engine in order to keep it mechanically viable. There's so much heat energy generated that without some sort of liquid energy exchange to cool the energy off or cool the engine off, the engine would fail because of all the crazy amount of heat that's being generated in the process of converting the gasoline into work. If you were an individual who could even up the percent efficiency of the internal combustion engine to even 40%, you would be a rich individual. Because believe me, the car manufacturers would be thrilled if you could pull these sorts of things off. Now, one of the reasons behind why there has not been such a major emphasis in improving the performance, it's not been so desperately important, is that there is a huge industrial complex behind the internal combustion engine. Humans have been working on the internal combustion engine for over 100 years. It was first made as a steam engine by Fulton and Watt and other individuals like that in the about the mid 1800s, we'll say. That's when the internal combustion engine was beginning to be worked on and improved. And of course, it really took off when we went from the steam engine to the gas-powered engine to drive the car industry beginning in the early 1900s. And of course, for the past over 100 years, the car industry has gone a long way to improve the efficiency of the engine, improve the gas mileage, improve this and that, the durability of the engines, all these things have been done. But because fossil fuels were relatively cheap for such a long period of time, there wasn't a crazy urge to upset the apple cart. Everybody was making money. The oil companies were making money. The car manufacturers were making money. So there was really no impetus to try to really improve the efficiency of the internal combustion engine. Now we're getting to the point where it's going to be more critical as we continue to exhaust the fossil fuels, as we continue to dump the carbon dioxide and other pollutants into the atmosphere from burning the fossil fuels. As we continue to do these things, we're certainly going to need to get away from our addiction to fossil fuels in order to maintain and sustain the things that we're doing. So again, I will point out, though, that for a long period of time, because of the cheap availability of the fossil fuels and the way the engines were designed to run the fossil fuels, there wasn't a large push to really improve the way that the engines worked in huge increments. We were very happy with small incremental change in the efficiency of these engines over this 150-year period. Okay, so let's look here at the other form of energy of motion. Notice energy of motion type number 6, I'm calling mechanical energy. That's work to move me up and down the road. It's a form of kinetic energy. Now the other form of motion, which is kinetic energy. Kinetic energy is motion. That would be heat. And as we will delve into here in a moment, heat is motion, just like work is motion. It's just the way motion manifests itself is a little different when energy is in the form of heat compared to when energy is in the form of work. All right, so one more time, I want to reiterate the definition of work is the ability to, scratch that. The definition of energy is the ability to do work or the ability to supply heat. So we are going to measure the energy content of a system from how capable it is to allow work to be done or how capable that energy source is to heat an object up. Now, work being done and heating objects up, again, are energy of motion. Work being done, heating an object up, is kinetic energy. All the other sources where we get the work from, where we get the heat from, are potential energy sources. They are storing it relative to the position of atoms or molecules in proximity to one another to allow them to store different amounts of this so-called potential energy. So electricity, electromagnetic, the gravity idea, the nuclear, stored in the nucleus, stored in the chemical bond, all these things are to be harvested, to be converted into either heat or work. So that's what we're motivated to do. Okay, so if an object absorbs heat, if an object heats up, when you put energy into it, we will term that as being endothermic. If an object gives off heat, we will term it as being exothermic. Now, how do we, again, gauge or measure these processes? We do so using a thermometer. That's our tool to tell us whether an object has more energy in it or less energy in it. So obviously then, when an object undergoes an endothermic process and you measure its temperature, its final temperature will be greater than its initial temperature. When an object undergoes an exothermic process, it is releasing energy. And our tool to measure heat energy is its temperature. So if an object undergoes an exothermic process, the name kind of implies it. Exo means external or outside. Thermic means temperature. So if it's exothermic, it's going down in temperature as it removes heat energy. If it's endothermic, it's going up in temperature as it gains heat energy. So often this is our only signpost. Now, again, there are other ways. You can measure it electrically by the voltage of it, and you can even measure it by speed of objects. But typically, in terms of the energy of heat, we're going to gauge the energy of heat content of a particular object based on its temperature. Okay, so one of the things you certainly should be able to recognize is when materials undergo the basic phase changes, what the energetics of those phase changes are. Okay, now let's maybe make some statements before we discuss these things. There's a distinction that chemists draw between phases of matter and states of matter. So let me just mention the difference between phases and states. Now, really, those terms are used pretty interchangeably when you speak normally, but there is distinct differences in what a scientist means by the phase of matter and what a scientist means by the state of matter. When we say the state of matter, we mean probably what you're thinking of for the phase of matter. The state of matter is solid, liquid, or gas. And of course, the gas is when they're practically invisible or they're spread so far apart. There are colored gases, yes. Some of them are transparent and clear. That's what we're most familiar with gas. And the reason they're transparent and clear is because the individual particles are so far apart that you see right through them. Then, of course, there's on the other extreme, the so-called solid phase, where the intermolecular relationships are so tightly bound that the object is rigid and takes up a fixed amount of space and doesn't spread through the whole container. A gas spreads through the whole container. A solid remains in a chunk sitting at the bottom of the container. The intermediate phase between solid and gas is this bizarre liquid phase, and it is rather bizarre, the liquid phase. It's really tricky. Believe me, scientists have fairly well-established models of solids. Scientists have fairly well-established models of gases, but we have a really tricky time establishing a really sound model of the liquid state because of its difficulty in getting a grasp. It's so dynamic and there's so much change occurring while in the liquid state that it's really pretty tricky to model. But in any event, probably I should have said here the energetics of state change, because we have the solid state, the liquid state, and the gas state. Let me just briefly mention to you what a scientist means when he says phase as compared to state. A phase is uniform in composition, but does not necessarily have to be distinctly different solid, liquid, or gases. Meaning, we have all seen two-phase liquids. Now, what do I mean by a two-phase liquid? All the molecules in the collection are in the liquid state, yet the liquid separates into distinct regions of that we call phases of the liquid. Now, where, of course, is the most obvious place you see this? In an oil and vinegar salad bottle. The oil is less dense than the vinegar. The oil sits on top of the vinegar. Oil and vinegar are a two-phase liquid state. So that's what really scientists differentiate when they say phase compared to state. Now, there are also multiple solid phases. An obvious example of multiple solid phases would be for carbon. When carbons are arranged in a certain way in the solid, they make what's known as graphite. And graphite to you would be the lead pencil in the lead pencil stuff. In your mechanical pencil, it's really not lead, it's actually graphite, and the graphite slides out of the pencil chamber really easily and deposits on the paper in thin sheets. But another solid phase of carbon is diamond, completely different arrangement of the structure of the carbon atoms in that particular solid phase. So it turns out that the pressure and temperature exerted on the carbon can put it into the solid phase known as graphite or the solid phase known as diamond. Now it turns out that that's not the only solid that has these kinds of designations of the way the solids are constructed. What you can think of is it's the way the atoms pack in relative to each other in the bulk sample. If you could look individually at each atom in the sample, you would see that they pack differently in the graphite phase compared to the way they pack in the diamond phase. That's what it boils down to. And again, pressure and temperature drives the way they're going to pack into each other. It's pretty obvious. Most of them pack in the graphite way. Very few of them pack in the diamond way because diamonds are much more rare. Okay, so having said that, and I apologize probably for using the word phase change here. I should have used the energetics of state change. And my state change is going to be changing from a liquid to a gas, from a liquid to a solid, from a solid to a liquid, and even from a gas to a solid or vice versa. So I'm schematically representing the equations of these state changes, we'll say, by little subscripts on the two symbolic representations on the reactant and product side. So the first one, if you like, to change the X into, say, H2O, that would be evaporating water. So I can have the equation H2O liquid becomes the H2O gas state. That would be evaporating. Now, I think it's not surprising to you that evaporating is endothermic. You have to put energy in to the liquid to change it into a gas. This is essentially what's going on in your clothes dryer. You turn on the clothes dryer, and if you don't put the heat on, spin the clothes around, yeah, eventually they will dry, yes. But if you put the heat on, you speed the rate at which the water evaporates dramatically. So putting the energy in the form of heat can speed up the evaporation process. Okay, now the next one has kind of a weird name. Probably your mom and them would call the changing of a solid into a liquid, they would call that melting. Chemists, particularly the British, refer to melting as fusion. So when I have a fusion process, I'm taking a solid into a liquid. Now, where you might envision what's going on here is when I'm welding two objects together, I'm fusing them. How am I fusing them? I take a solid piece of solder, melt it to a liquid, and then when the liquid re-solidifies, I have fused the objects together. So fusing two solids together is caused by melting something that then when it solidifies, connects them back together. So that might be the source of how you can think of the name fusion. Now notice that fusion is also an endothermic process. Now, of course, what that again means is you must put energy in to invoke these endothermic processes. All right, now think about the state of the matter too. In the solid state, the atoms are locked onto each other. In order to get to the liquid state, they have to have more mobility, more freedom to move independent of one another. If I increase their energy, now the attractions they feel for each other do not grab each other strong enough so that they can move independent of each other easier. So by adding more energy to the solid phase, they can now live in the more independent liquid phase. And same thing with the one above. Liquid phase molecules have this independence, but now when I add more energy to them, they are really free of each other. And as long as I keep them at this elevated state of energy, they can remain independent of each other in the gas form. So gases take more energy to maintain than do liquids. Liquids take more energy to maintain than do solids. So if I want to go from a liquid to a gas, I have to input energy. If I want to go from a solid to a liquid, I need to input energy. Now the last one, at least the third one, the third one is a little bit weird. It's a little less familiar to us, but it is also a very important process. It is known as sublimation. So really, when we certainly think in terms of, say, the liquid state of water or the solid state of water, we don't think of solid ice going directly to gaseous steam. We always pass through the liquid state on the way. Well, there are other materials which do not do such things and which actually go straight from the solid to the gas. And when a material sublimes or sublimates, it goes straight from the solid to the gas. Now, as a matter of fact, this is endothermic as well. The more ordered solid state converted into the gas state is dependent on input of energy because of the looser association that molecules in the gaseous state possess for one another. As long as they don't feel each other, if they're moving more dramatically, that's probably what you should think of. They're moving more dramatically, they're in the higher energetic state. Now they can't stick to each other into the solid phase. Okay, now another thing that we should mention here is that because energy is conserved, there's going to be some additive property between going from a liquid to a gas and a solid to a liquid. If I add those two together, that would tell me something about the energy of going from a solid to a gas. I'm just bypassing the liquid stage when I undergo the sublimation. But the energetics to pull it off are going to have to be some combination of the energy of going from the solid to the liquid and then the liquid to the gas. Okay, so the first three are going from a more ordered state to a less ordered state. And the first three are endothermic. They require energy to pull them off. Now the third, or the bottom three, if you like, are all going from more ordered to less ordered. Scratch that. They're starting in the less ordered form and going to a more ordered form. And in order to get them to the point where they're sticking to each other more cohesively, you must remove energy. So in the final three processes, the act of pulling them off is an exothermic action. So if I want to condense a gas, I have to remove energy from the gaseous state to get it into the liquid state. So that is exothermic as I condense the gas. It is exothermic as I solidify a liquid. I remove energy from it. Now the molecules are moving slower. When they're moving slower, they can stick to each other more effectively. When they stick to each other more effectively, they can form a solid. And then lastly, I have what I call deposition. If you like, depositing. Depositing is, again, the weird case, which, again, we don't have huge familiarity with because there's not many materials that commonly do this under the conditions that we live in. But if materials deposit, they go straight from the gas directly to the solid, bypassing liquid. Now, I will mention where this is of utmost importance. This is of great importance in the semiconductor industry, in the transistor industry, in the high tech industry where we print out computer circuits and tiny devices. In order to get the metals of the right composition to plate out onto the circuit boards, they put them in these certain rooms where they have the materials in gas phase, and then through some wizardry of using electric and magnetic attraction and quick change of temperature, they depose gaseous materials directly as solid materials to print transistor circuits. Now again, all three of these processes are exothermic, meaning energy must be released when you either condense, solidify, or depose materials. Now here's another very important statement with regard to the energetics of these kind of changes. That would be that these are reversible in all senses of the word. Meaning that, let's suppose I have 10 grams of liquid water and I want to evaporate it. I have to put a certain amount of energy into the 10 grams of liquid water to evaporate it. Now let's suppose I have 10 grams of gas phase water and I want to condense it. I must remove from the 10 grams of water exactly the same amount of energy that I put in to take the 10 grams of liquid water to the gas phase. So these are, if you like, reversible values. Whatever energy you must put in to change a certain material from the solid state to the liquid state, that will be exactly equal to the amount of energy I will get back if I change the liquid state to the solid state. Same thing is true with any of these others as well. The amount of energy required to evaporate a certain quantity of liquid will be exactly equal to the amount of energy I will get back or will release when I condense the same amount of gas back to liquid. So energy in nature works very conservedly, meaning whatever it takes for you that you have to put in to make a process go would be exactly the amount you would get out for the reverse process. So like for instance, when I want to put a book on the third shelf, I have to do a certain amount of work to lift the book to the third shelf. If you remove the shelf and the book falls to the ground, then gravity does an amount of work equal to the work I put in to lift the book up to the third shelf. Okay, so let's now focus on this sensible form of energy when heat is present. As I've already indicated to you, heat is in some way motion of the matter, and as the matter is moving, it contains energy, and how we sense the energy that is present in this matter would be simply by measuring its temperature. The hotter the temperature of the matter, the more heat energy content that, of course, the matter possesses. So heat, of course, as we said, is a form of energy. It's, in fact, a form of kinetic energy. And if it's a form of kinetic energy, it is energy of motion. Now, in particular then, let's think of the situation of how we can use this idea of temperature in connection to the amount of energy that the object possesses. So let's just, for instance then, think of two benches in the park. and let's say neither of them is in the shade. They're both sitting out in the sun in the park, and you go over and you touch the wooden bench and you say, "Whoa, that's warm," because the sun is beating down upon it. Then you go over and you touch the metal bench and you go, "Whoa, that ain't warm, that's hot." So there's a much greater temperature in the metal bench than there is in the wooden bench. Now, when you stop to think about it, that's a little bit weird, from the simple fact that the metal bench and the wooden bench are really receiving the same amount of heat energy from the sun. The sun is 93 million miles from the wooden bench. The sun is 93 million miles from the metal bench. The same radiative heat is coming from the sun, striking the metal bench as is coming from the sun and striking the wooden bench. So there's obviously some differences that are making the wooden bench feel cooler than the metal bench. So there's something to the constitution of how the atoms of the wooden bench are stuck together compared to how the atoms of the metal bench are stuck together, such that if you put a thermometer on both of them, the metal bench will register a ridiculously higher temperature than the wooden bench. Okay, so maybe first of all, what we should think about is, what does heat mean in the first place? Heat is motion. Heat is kinetic energy. Work is motion. Work is kinetic energy. So what is the difference between motion in the form of work compared to motion in the form of heat? Now, again, before we go anywhere, let me remind you, these are our desirable forms of energy. In the definition of energy, it is stated, energy is the ability to do work or the ability to supply heat. This is what we want. From energy, we want work or heat. But now, according to these definitions, they're really the same thing. Work is kinetic energy. Work means matter in motion. Heat is kinetic energy. Heat means matter in motion. So there must be some difference to the way that the motion manifests itself in heat compared to the way the motion manifests itself in work. And quite simply, when an object is hot, it is moving. But the key is that it is moving completely randomly. Meaning, if you could now nanoscopically look at the matter, you would see a collection of atoms moving. The hotter the matter is, the more dramatically they're moving. But now look at how they are moving. The matter is a collection of a huge number of molecules, and there's a certain number of them moving up and down and up and down and up and down. While that is happening, there's a certain number of them moving down and up and down and up and down and up, meaning, well, this one's going up, that one's going down, and vice versa. Now, there's a certain number of them moving left and right and left and right. But for the same number that are moving left, there's an equal number moving right, and vice versa. And some are moving diagonal, 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 this way, that way, this way, this way, this way. And for heat, the motion is completely random. For every molecule moving up and down, there's one moving left and right. For everyone moving left and right, there's one moving diagonal, and so on and so forth. Exactly the same amount of molecules are in this motion in all directions simultaneously. Now, the hotter the object is, the more dramatic they are moving. That's where the kinetic energy comes in. The hotter it is, the more they're moving. The colder it is, the slower they're moving. So you cool it and cool it and cool it. They move slower and slower and slower. You heat it and you heat it and you heat it. They move faster and faster and faster. But the key with heat is that it's all random, each way exactly equally likely. Now let's contrast that to the kinetic energy of work. Kinetic work is kinetic energy, work is moving. But now all molecules move concertedly, meaning all molecules move in the same direction. When I get behind the block and I push, every molecule in the block is moving in the same direction. There's not some moving up, some moving down, some moving left, some moving right. Concerted motion is work. Random motion is heat. Now, the faster I push it, the more kinetic energy I'm putting, but I'm putting more kinetic energy in a concerted form. The more I heat it, the more randomly they're moving, but the more randomly they're moving so that all are equally likely. And as a matter of fact, when you look at it externally, you don't see the object moving. The hotter I make it, I don't see it dancing around. That's because all its internal movements are canceling one another. Okay, so it looks to me like as if that would be the quitting time. Remember, go to Moodle, do test 3, part 3. It will be open until Wednesday, 11:30 of next week, November 25th. So until Monday of next week, peace out.